We're going to spend a few days looking at what we call, quote-unquote, modern physics. In physics, we tend to break overall physics up into two categories: classical physics and modern physics. And modern physics really began right around the 1880s and 1890s as they were trying to figure out what were called quantum phenomena. That's what we call them now. And it really birthed itself in 1905. I think it was 1905, when Einstein published special relativity. What we've been doing so far is what we call classical or Newtonian physics. We say Isaac Newton is the father of classical physics because he made a lot of discoveries, but he didn't realize that actually the physics that he was studying, classical or Newtonian, is part of a more special group, modern physics. Now, most of the modern physics stuff only needs to be dealt with when you're really small, at the atomic level, or at the smaller than atomic level, at the subatomic proton, neutron, electron level, or when you're going really fast. We're going to be talking about what happens when you're going really fast. In fact, really, what we're going to be talking about is, what's the big deal with Einstein? Why is he so revered? And I'm going to try and walk you through sort of what he was thinking about when he was in high school, because most of his discoveries originated with questions he asked himself in his high school physics class. One of the first ones he asked himself was, what would I see if I was riding on a beam of light? Because I use light to see things, but I'm traveling at the speed of light. Would light bounce off other objects back to me? Or because I'm traveling at the speed of light, would everything just be kind of frozen in place? Or would, And it was this question that started him thinking that maybe light was special, and it is very special. So here's our thought experiment. I'd like you to imagine that we have a cannon that can launch a baseball at exactly 30 meters per second every time. And we're going to have a back catcher, Sam, standing right here. Here's good old Sam. He's holding a baseball glove, and what would he see if he was standing still? So we have the cannon, boom, launch the baseball at 30 meters per second. Relative to Sam, how fast will the baseball be traveling? This isn't meant to be a trick question. This is how most of you think about velocity. Since Sam is standing still and the ball is coming to him at 30 meters per second, Sam will see the ball traveling at 30 meters per second. We're going to repeat the thought experiment, but this time the cannon is going to be on the roof of a big van traveling towards Sam at 15 meters per second. So the van is moving at 15 meters per second. Bang, we fire the cannon at 30 meters per second. How fast will the baseball arrive relative to Sam? 45. Because it's going to have the speed of the van and the speed of the baseball. This is why, for example, if you want to throw something really hard, you might take a running start and throw it on the run, because your running velocity gets added to the baseball velocity. This is why quarterbacks don't like fading back to throw, because if you're running backwards and you throw, you're taking velocity off the football. In fact, let's do that little thought experiment. Same as situation number one, but this time the van is traveling backwards. The cannon fires forwards at 30 meters per second. How fast will the baseball be traveling relative to Sam? 15 meters per second. So far, so good. I don't think we've turned the page yet. There's lots of reading and things to think about. Now we're going to go cosmic. There's a very famous experiment that's called the Michelson-Morley Experiment. In the late 19th century, right around 1895-ish or so, two physicists, A.A. Michelson and E.W. Morley, conducted an experiment. They thought that they could do this cannon analogy with light coming at us from a distant star. So here was what they're thinking. we have light coming at us from a distant star. That's the baseball. And they said in January, the Earth is moving towards the star. In July, the Earth is moving away from the star. There should be a difference in the speed of light, the same way there was a difference in the relative speed of the baseball. There should be a difference in what we measure as light speed. In January, it should be light speed plus the Earth's movement. And since the Earth moves fairly fast around the sun, they thought we can measure that difference because light goes so fast it's really tough to measure. But they thought this we can measure. We think we can measure it. Oh, and in July, when the Earth is moving away from the light, that's sort of like having the van moving backwards. The speed of light should be slightly less when it gets to us. You okay with that? So here's what I wrote. They thought they could measure the difference of the speed of light hitting the Earth in two situations. And they decided to measure the speed of light hitting the Earth when the Earth is moving towards a distant star, like here, and the speed of light hitting the Earth when the Earth was moving away from a distant star, like here. And they figured they'd get two very slightly different answers. Here's the picture. This experiment is called the most famous null result in history because when they performed the experiment, they got the same answer both times. Light did not behave like a baseball. And this confounded them. In fact, Morley went to his grave, he died, believing they'd botched the experiment. For 20 years, he actually argued against his own result. He said, I think we did something wrong, because light should behave like a baseball. It was so weird to think that light behaved differently from anything else we'd seen at that time. So, the expected result didn't materialize. Instead, they got the same speed of light for each situation. It was like situation number 2 and 3 above giving the same answer. It would be like you got 30 meters per second for both of these here. Huh? And so here is the conclusion. Light is special. It is. And the speed of light is a constant for all observers. The conclusion of this experiment was, no matter how you measure the speed of light, whether you're moving towards the object sending the light towards you, or moving away from the object sending the light towards you, for some reason, when you try and measure the speed of light, you get the same answer. We say it's a constant. This is the speed of light in a vacuum. You can change the speed of light because it goes at different speeds through different objects. Light slows down through glass, light slows down through water. But in a vacuum, the speed of light is the same no matter how you try and measure it, whether you're moving towards the object or away from the object. So the MickelsonMorley experiment is famous for its negative result. It showed experimentally that the speed of light in space, in a vacuum, is the same for all observers, regardless of their velocity or the velocity of the source of light. Now you can turn the page. The speed of light does not depend on your frame of reference at all. No evidence could be found that space could be used as a fixed frame of reference. That doesn't sound that profound, hugely profound. So, the speed of light is a constant. What letter does the word constant begin with? So we use a lowercase c as our universal symbol for the speed of light. How fast is the speed of light? It's actually quite a nice number. The speed of light is 3 times 10 to the 8th meters per second. That's 3 with 8 zeros. That's the speed of light in a vacuum, in outer space. So along comes Einstein. Einstein knew about this result, and there was much debate on how to explain it. Some people said, well, their equipment was flawed. The experiment was bad. Einstein came along and he said, what if their experiment was good? What if light is a constant? And what does that mean? And he got very basic. He went right back to physics 11. He said, wait a minute, if speed is distance over time, because light has no acceleration, it's instantly at full speed, so you would use d equals vit plus a half at squared, but the half at squared would vanish and get the v by itself. If v is d over t, or, wait a minute, since we're going cosmic, if speed is space over time, then how can we always have the same speed as an answer, no matter what situation we throw at light? And here's where Einstein went, got it. That must mean that space and time change depending on the situation. Nobody had ever considered that before. We all thought at that time that time behaved the same for everyone. And Einstein said, well, look, if light behaves this way, then space and time can't behave the way we thought. Put your pencils down, look up. How did this experiment transform science, you might ask? Let's keep going. Because, Christina, light is what behaves weird, this was Einstein's next brilliant move. He said, well, why don't I use light as my timer and as my clock? If this is what I'm trying to figure out how it behaves, rather than use a clock like a watch, I'll use a light timer. I'll use as a timer flashes of light. That'll work. So here's situation number one. I want you to consider a spaceship hovering at rest relative to the Earth, like in that little picture. See it? It's going to send a brief, regularly spaced flash of light to Earth. Some amount of time will elapse before the flashes get to the planet. It takes 8 minutes for the light from the sun to hit the Earth. So we'll put this spaceship out in space, and it'll take a while for the light to reach the Earth. But we're going to send a flash every 6 minutes so that on the Earth, they'll see the flash every 6 minutes, and they can set their watch and they can count the number of flashes. So they're going to measure the flashes 6 minutes apart. So 2 flashes would be how many minutes? 2 times 6 in your head is 12. 3 flashes would be 18 minutes. Okay, so we're going to use light as a timer. With me so far, Darcy? With no motion involved, nothing unusual about this. So, if the flashes are every 6 minutes, we're going to do some math in our head, Haley. In 60 minutes, the ship will send out how many flashes? You're right, say it loud. 10. And the Earth will see 10 flashes. Now, let's start moving fairly fast. Situation number 2. When speed is involved, fill that in. The situation is quite different. Now, here is the important thing. The speed of those flashes will still be, what's the letter C an abbreviation for? The speed of, okay, let's make a little note here. C equals the speed of light. It's not an abbreviation for constant. We used C because light is a constant. Okay. This is what Einstein proposed. No matter how the ship or the receiving planet might move, how frequently the flashes are seen, however, very much depends on the motion involved. When the ship travels toward the receiver, if the spaceship is coming towards the Earth really fast, the Earth would see the flashes more often, and this is because, not only because time is altered, which we'll talk about, but mainly because each succeeding flash has less distance to travel. Like in this picture here. Because this spaceship is moving closer and closer to the Earth, every time it emits a flash, since it's moved closer to the Earth, the flash has less distance to travel, and it'll get to the Earth a little quicker. A little quicker, a little quicker. So, suppose the spaceship emits a flash every 6 minutes, but it's going so fast that on Earth we see the flashes every 3 minutes. What would happen? In 60 minutes, how many flashes will the ship emit? 60 minutes, every 6 minutes, do the math in your head. 10 flashes. How many flashes will the Earth see? 10 flashes. However, how much time does the Earth see between flashes? So the Earth, each flash will arrive 3 minutes apart. How long will it take the Earth to see the 10 flashes, which took the ship 60 minutes to send? 10 times 3. Only 30 minutes will have elapsed on the Earth, even though 60 minutes will have gone by on the ship. And that's not a trick, that's not a math trick. The clocks would actually physically read differently. We pause and reflect on how weird and cool our universe is. And then we can turn the page. What if the ship is going away from the Earth? If the ship is going away from the Earth and still shining the flashes back, because, Linnea, it's going away from the Earth, every flash has a little further to travel. So even though the ship on its clock is sending out flashes every 6 minutes, let's suppose, we'd have to set this up just right, Jenna, that the ship is going at just the right speed so that the flashes are arriving back on Earth every 12 minutes. So the effect of moving away is just the opposite. If the flashes are received twice as frequently when the ship is approaching, 6 minutes turn into 3 minutes. They are received half as frequently when it's receding. 6 minutes turns into 12 minutes. So here we would have 10 flashes times 6 minutes on the ship. 60 minutes would pass. But how long would the Earth take to measure those 10 flashes? 10 flashes times how many minutes apart are they on Earth? On the ship, you would have gotten 1 hour older. On the Earth, you would have gotten 2 hours older. This is not a math trick. This is how time actually behaves when you start moving really fast. And why? Because the speed of light is a constant. So here's our conclusion. If two events are separated by 6 minutes according to the spaceship clock, they'll be seen on Earth to separated by 12 minutes when the spaceship recedes, moves away at a very high speed. And by only 3 minutes when the ship is approaching at a very high speed. And this leads us to something that we call the twin paradox. Let's suppose you have two identical twins. One twin is an astronaut. I'll call him twin A for astronaut. And he's going to take a high-speed round trip journey in the galaxy, while the other twin stays at home. Youngjun, I'll call him twin H for home, on the Earth. When the traveling twin returns, he's actually going to be physically younger than his twin brother. How much younger depends on the relative speeds involved. This is why, by the way, unless we do invent a Star Trek warp drive technology, which is unlikely, if you're wondering about the future, if we do space trips, they will all be one-way trips, because by the time you arrive at your destination, everybody back home will long since have died. People that you know, your relatives, your loved ones, your friends, will long since have passed away, because time will be moving slower for you than it is back home. We're going to prove it. So here's a picture summary. Let's actually walk through some numbers. Let's apply this doubling and halving of flash intervals to these two twins. Supposing the twin recedes from the earthbound twin at the high speed for 1 hour, and then turns around and returns in 1 hour. We're going to follow this line of reasoning with this figure up here. So the traveling twin takes a round trip of 2 hours, according to all the clocks aboard the spaceship. But on Earth, the trip will not be seen to take 2 hours. It'll be seen to take longer. How will you figure that out? It's all about the light clock. So here's a big chart. We're going to fill this in. This is our homework. We're going to do it together. On the ship, we're going to send a flash out every 6 minutes. And to make it easy, Darcy, we're going to start right at noon. So 12:06, flash. What would 6 minutes later be? So let's fill in here 12:12, flash. I'll make this bigger. And then the third flash, 6 minutes later, the clock would read 12:18. 6 minutes later, the clock will read 12:24. 6 minutes later, the clock will read 12:30. Nothing dramatic so far, but let's keep going. 6 minutes later, the clock will read 12:36. 6 minutes later, the clock will read 12. Do the math. No. 42. Then 12 minutes later, the clock will read 12:48. Then the clock will read 12:54. 10 flashes is exactly for this person 1 hour. You know what? Just to make the math easier, let's go military time. Let's call it 1,300 hours instead of going down to 1 o'clock. Let's go 1,300 hours because that just makes the math easier, okay? Let's go over the next column. Then we have 13:06, 1:06. 6 minutes later, 13:12. 6 minutes later, 13:18. 6 minutes later, 13:24. 6 minutes later, 13:30. And then 13:36. 13:42. 13:48. 13:54. When the astronaut on the spaceship gets back, what will his spaceship clock read? 1,400 hours, or 2 p.m. As far as the astronaut is concerned, his trip lasted 2 hours. With me so far? What does the Earth astronaut, the twin brother, experience? So let's go back to the beginning. Right here, they've shaken hands and they've synchronized their watches. You're leaving at noon. I'll see you later. Mark. Now, going away from the Earth, the flashes are going to take longer to get back to the Earth. The Earth will see the flashes every 12 minutes. So because the astronaut is going away at the beginning, the Earth sees the first flash arrive at 12:12. Flash. The Earth sees the second flash arrive at 12:24. 12 minutes later, because the ship is moving away, so the light has further to travel each time. We're going up by 12s now. What's the next time going to be? 12:36. What's the next time going to be? Sorry? What's the next time going to be? 48. What's the next time going to be? 1,300 hours. 13:12. 13:24. Right? 13:36. 13:48. 1,400 hours. Now the astronaut turns his spaceship around and starts heading back towards the Earth. Now, because he's heading back towards the Earth, the flashes have to travel a smaller and smaller distance so that they actually get there faster and faster. Now the Earth is going to see those flashes arriving every 3 minutes. So we started with 1400, and now we're going to see the flash at 1403 every 3 minutes. What's 3 minutes past 1403, Taylor? Yep. Then 1409 plus 3, 1412 plus 3, 1415, 1418, 1421, 1424, 1427, and the astronaut arrives back on Earth, and the astronaut's clock says 2 hours have passed. How much time passed on the Earth? 2.5 hours. His twin brother is half an hour older than him, and that's not witchcraft, that's not fancy math speak, that is how the universe works. Any object that is moving experiences time slower than any object that is at rest relative to that object. Yep, everything's slower. Age slower, absolutely. Absolutely. Now, the only problem, Thomas, with this method that I've just done with you is it's tedious. It turns out, next class, Tuesday, we'll see there is a way to just calculate this with an equation without having to walk through every individual 3-minute or 6-minute or 12-minute step. You can get straight there. In fact, I'll even prove to you how Einstein proved it. We'll redo his paper. One of the reasons we like Einstein so much is, as smart as he was, his thoughts are very simple. He proved this with Pythagoras, with Math 8, with a very elegant idea. We'll show how that works. So Thomas, is it possible to travel through time? We just did. The astronaut traveled 30 minutes into the future. The astronaut traveled 30 minutes into the future of his twin brother, because his twin brother is 30 minutes older. So special relativity tells us we can travel into the future, but not into the past. Put your pencils down, look up.